So let's go ahead and start. But before I do, does anybody have any questions? All right. So if you guys remember, last time we started looking at galvanic cells. And simply put, galvanic cells take advantage of a spontaneous redox reaction. And we're going to take advantage of a spontaneous redox reaction to generate a flow of electrons through a wire. And we looked at the experimental setup for the galvanic cell shown here. We call this the Daniell cell. And the Daniell cell is made up of two electrodes. We have a zinc electrode and a copper electrode. The zinc electrode is the anode, and the copper electrode is the cathode. And so instead of specifying the electrode, you could also use the redox couple, all right? It's like the conjugate acid-base pair. And always when you list out a redox couple, you list it so that you have the oxidized form first, and then a diagonal line, and then the reduced form. So if you look at the redox couple for the zinc electrode, it will be zinc 2 plus zinc. If you look at the redox couple for the copper electrode, it would include copper 2 plus and copper. And as all of you know, the anode is the site at which the oxidation takes place. The cathode is the site at which reduction takes place. And so if the oxidation takes place at the anode is the point at which electrons are lost from the cell, because when oxidation takes place, electrons are being produced or generated, and these are being pushed through that wire, all right? At the other end, we have the cathode. The electrons are being pulled into the cell, all right? And so the cathode is where the electrons enter the cell. The anode is assigned a negative sign because it's the site at which electrons are being generated through the wire. It's going to be pushed through the wire. And the cathode has a plus sign to show that the electrons are entering the cell. And then if you were to write the two half reactions, the oxidation half reaction, you can see the two electrons that are produced. And on the reduction half reaction, you can see that the two electrons are taken up. If you want to write the net reaction would be the sum of the two. And now you can look at the net reaction, and overall, the net reaction summarizes what's going on overall in this galvanic cell. Okay? And then lastly, we looked at the fact that we have a shorthand notational scheme that allows us to summarize this entire picture that I've drawn up there can be summarized in just using this notational scheme. So what I need you to be able to do is be able to look at a picture and write down the cell notation, which describes it, or vice versa. If you see a cell notation, then what you need to be able to do is have a mental picture of what that cell is going to look like, what the setup should look like, and how the whole cell is constructed. Okay? So you should be able to fluidly look at notations, just like when we said when we use in balanced equations, when we use chemical symbols, they actually represent pictures at a macroscopic or a microscopic level. All right? So you should, just as when you see copper solid, you know that means it's metallic copper. At a microscopic level, you should know that it's a giant structure of just copper atoms bonded to each other, forming a giant structure. All right? Likewise, when you see a cell notation of this type, you should immediately have a mental picture of what that cell looks like. Now, we finished up at the end of the class looking at some examples of cell notations, and I'm just going to continue doing that. So this just summarizes what we looked at last time. Now we're going to proceed to looking at some other examples of cell notation. So if you take the hydrogen electrode, let's write, so if I take the hydrogen electrode, so overall it's called the hydrogen electrode. And if you take the hydrogen electrode, the cell notation that describes that is H plus H2. So that's the redox couple. Sorry, this is the redox couple that describes the hydrogen electrode. Okay? Now the hydrogen electrode could be a cathode. Remember, if it's the cathode, it is the site of the reduction. So you would have 2H plus aqueous plus 2 electrons, giving you H2 gas. So because it's a cathode, this would represent a reduction. All right? And so if you were to use the cell notation for the cathode part, then remember for the cell notation, you always start with the reactant first and then the product. So the reactant here is H plus aqueous. Now if there's a change in phase, then you put a vertical line. So we're going from the aqueous state where it's soluble in aqueous to a gas. So there is a change in phase, so there's going to be a vertical line to give you hydrogen gas. But as all of you recognize, for the hydrogen electrode, because both one is in the aqueous phase and the other is in the gaseous phase, you need some inert metal to bring the electrons into the cell. All right? And so we said a common inert metal that we use in electrochemistry is platinum. You can use things like carbon fiber and so on. And because we have to have an inert metal bringing the electrons in, we're going to put that at the end. All right? And so this would be the notation for the hydrogen electrode if it were the cathode. Now if I was to write then, if it turns out the hydrogen is the anode, now this is the site of the oxidation. So now the reaction would be where electrons are being generated, and so you would end up with that. And so at the anode we have an oxidation. So now if I were to write the cell notation for this, because now we're at the anode end, when it's the anode, you start with the inert metal first, and then you write down the reactant, which is H2, and then H plus aqueous. Okay, so if you're using an inert metal to bring electrons into the cell, if it's an anode, you always start with that. If it's a cathode, you always end with that. So it's kind of at the both ends, okay? So the inert metal that is used to bring electrons in are put on the extremes on either side, okay? So if I were to look at the general reaction, so remember we looked at two types of cells last time where we have the hydrogen electrode. So if you take this, so what I have here, the first part is the electrode where you have zinc electrode on one side, that's the anode, and the hydrogen electrode is the cathode where the reduction takes place. So if you want to write the net reaction for this, you know that the net reaction would be zinc solid plus, this is the reduction, so you're going to have 2H plus aqueous giving you zinc 2 plus aqueous plus H2 gas. All right, so where this is the anode where the oxidation takes place, this is the cathode where the reduction takes place. So the cell notation for this would be, we start with the anode, which is zinc 2 plus. This is the reactant product, and use a vertical line, not a diagonal line. The diagonal line is reserved for redox couples, okay? And then now we have a salt bridge, so we're going to bring in the salt bridge. Now we're going to write the cathode. The reactant for the cathode is H plus aqueous, vertical line because you have a change in phase going to H2, and then from the gas you have a change in phase as you go to the solid material, platinum. And that will be the cell notation. So when you see the cell notation, it translates to the picture that's drawn there. Okay? Now, if I move on to this cell on this side, so if I go to this side and look at this cell, now you can see that the hydrogen electrode is the anode and the copper electrode is the cathode. All right, so this is the site of the oxidation. So that means the net reaction here would be H2 gas, all right, plus copper 2 plus aqueous, giving me 2H plus aqueous plus copper solid. Okay, so this is the reduction half reaction. This is the oxidation half reactions. 2 electrons are being transferred. All right, and therefore the cell notation should be, now remember the hydrogen electrode is the anode, so we start with platinum, then we have hydrogen gas, vertical line, H plus aqueous, 2 vertical lines for the salt bridge. And then on the other side, I would end up with the reactant, which is copper 2 plus aqueous, vertical line, copper solid. All right, so if you use the hydrogen electrode, depending on whether the hydrogen electrode is the anode or the cathode, you would write the cell notation in this way. Remember, you have to keep in mind these are all galvanic cells, and we only take reactions that are spontaneous. So both of these examples that we look at are spontaneous reactions, all right? And that will be the cell notation. Now, one last thing I want to show you is if we take another example of another electrode, okay? And let's take the example of, let's say I have this electrode. So the redox couple here is I'm going to look at ion 3 plus, ion 2 plus electrode. All right, so if I have this, then if this were the cathode, you remember at the cathode is the site of a reduction. So we're going to write the equation in the form of a reduction. That means you have ion 3 plus aqueous plus 1 electron, giving you ion 2 plus aqueous. Remember, your half reactions have to be balanced. And one way to quickly check whether your equation is balanced is atom balance, 1 ion, 1 ion. Now you have to have charge balance, so you have 3 plus minus 1. So this is 2 plus on this side. For the overall charge on that side will be 2 plus, and therefore you have charge balance as well. And because electrons are being picked up, this is a reduction. All right? So if you look at this, you have ion 3 plus aqueous and ion 2 plus aqueous. So both of these, neither of these are metals. Both of these are dissolved ions. So can everybody see that means if I want this to act as a cathode, I need something to deliver the electrons to the cell. And so I need an inert metal to deliver the electrons to the cell. And therefore, the cell notation for this would be my reactant, which is ion 3 plus aqueous. Okay? Now, if you look at this, there is no change in phase. They're both aqueous. They're in the same phase. Therefore, when you have the same phase, then you use a comma to indicate that they're in the same phase. You only use a vertical line if you have 2 different phases. Okay? So I'm going to use a comma there, and then I'll have Fe2 plus aqueous. Now I have a change in phase because I'm going to bring the platinum metal, and that's what this would look like. Okay? If this were the anode, now you would have the oxidation, so this would be Fe2 plus aqueous plus an electron, giving me Fe3 plus aqueous. So this would be the oxidation. Now since it's the anode, we're going to start with the inert metal that delivers electrons, then my reactants, which would be Fe2 plus aqueous, comma, Fe3 plus aqueous. Did you guys get that? Because they're both in the same phase, now we use a comma. Yes?
No electron on the other side.
Oh, we're looking at oxidation. You're right. I'm sorry. I've written it in the form of reduction. Thank you. It should be right here. Okay? So that will be, so you're producing electrons. And one way to quickly check whether you've made a mistake, I'm writing this really fast because I do want to finish this topic today. But one way for you to quickly check whether that equation is balanced or not is to do an atom balance and a charge balance. And you'll find that if I had put the electrons on the wrong side, ion 2 plus electron will give me plus 1. So on one side I have plus 1, on the other side I have plus 3. Therefore I know that the equation is not balanced. Okay? And this is an oxidation, so electrons are being produced. Okay? Now, so if you want to take an example of this, if you take the reaction where you have zinc solid plus 2 Fe3 plus aqueous, because remember each one of these produce 2 electrons. If this is the reduction, then they're picking up 2 electrons. So zinc produces 2 electrons where the oxidation takes place, and you need 2 of these to balance the electrons. All right, because each ion only, if the ion is undergoing a reduction, each ion picks up only 1 electron. So you need twice as many. So to balance this equation, you have to have zinc 2 plus aqueous plus 2 Fe2 plus aqueous. Okay, so this would be the net reaction that we're looking at. And if this were the reaction that we're looking at where zinc is, this is the anode, this would be the cathode because this is the reduction. 2 electrons are lost by zinc and 2 electrons are being picked up by iron. That's why we're multiplying it by 2, the coefficient's 2. Okay? So that would be the balanced equation. And then if I want to write the cell notation for this, my anode would be zinc electrode. So that would be reactant, product. Now I need a salt bridge. And now my cathode would be where I have my reactant, which is Fe3 plus. So I'll have Fe3 plus aqueous. Now a comma because they're both in the same phase. Fe2 plus aqueous. And then a vertical line and platinum. Got it? So I've taken a lot of examples to show you how to write the cell notations. Now, your online homework is going to get you to write cell notations. Now, this online homework will be a little frustrating because you have to use those vertical lines, commas. So the online homework is actually going to check to see whether you're putting a diagonal line or a vertical line, whether you put the comma at the appropriate place. All right? Spacing will become important, but it's a good practice. All right? And so, and it'll tell you how to put those symbols in, how to type it in. Okay? So please follow the instructions carefully, but it's a good exercise because after you do 5 examples, all right, you'll be pretty good at it, but you will also find it very frustrating. All right? Because remember, computers are not smart. It's going to look to see whether you're typing in the correct symbol in the right way. Okay? Yes?
But do we need to put the phases in there when we do this?
Yes, you need to indicate the phases. All right? On an exam, because that's how you can tell whether they're in the same phase or whether they're different phases and so on. That's how you can tell whether you're going to have a vertical line or whether you're going to have a comma. All right? Yes, go ahead.
Do we need to include the coefficients or do we leave those out?
You do not include coefficients for cell notation. All right? For cell notations, you only identify the species. All right? The coefficients are only to balance equations. All right? You don't even include the coefficients when you look at redox couples. Redox couples identifies only the reactant and the product, the oxidized species and the reduced species. Okay? So the only time you use coefficients is when you balance equations and when you try to figure out how many electrons are given off and how many electrons are taken up. Okay? So I want to warn you ahead of time. Give yourself ample time when you do that homework on cell notation because you are going to be frustrated because it's all about how you type it in. All right? If you type it in incorrectly, if you put an extra space where there shouldn't be a space, it's going to mark you wrong and you're going to look at it and say, you know, what's going on? Okay? Also, there's a difference between the number 0 and the letter O. A lot of people in this unit, when they write H2O, they, you know, if you accidentally put the number 0, because we're using the Geneva font, you can't tell the difference between the number 0 and the letter O, okay? And so make sure you type it in. So it'll keep marking you wrong, and you just can't figure out why it's marking you wrong. And the reason is that you're typing in the number 0 rather than the letter O, and vice versa. Got it? Okay. Yes, go ahead.
Is the cell notation does not include the H2O?
Unless, yes, you do not include it if it's aqueous solution. Unless H2O is part of the reaction where water is being produced or something like that. Got it? If it's an aqueous solution, you do not include the solvent because the solvent is in large amounts. It's there in the background. And that's what AQ means. When you put within parentheses AQ, that's what that indicates. All right? And so you do not include the water unless it's part of the balanced equation. Okay? All right, so now that we've looked at cell notation, now we're ready to look at cell potential. So we're going to look at cell potential, voltage, or electromotive force. All right, all 3 terms mean the same thing. And the symbol that we're going to use is E. So we're going to use the symbol E subscript cell, and this refers to the cell potential or voltage or electromotive force. Now remember, whenever we set up a galvanic cell, like the one shown here, we said that we attach a voltmeter and we measure the voltage. So at time equals 0, the instant you started and if you complete the circuit, the voltage that you measure will be the cell potential. All right? And as electrons start flowing, as current starts flowing, what happens is over time, you'll notice that your cell potential gets smaller and smaller. So at t equals 0 is when the cell potential will be the highest. And then after a while, as this reaction proceeds and proceeds and proceeds, the voltage will start decreasing. And at some point, it's going to go to 0. And that means now your cell is spent. And the analogies, remember, galvanic cells are batteries. And that's what happens when the batteries that we use after a while, the batteries get spent. All right? And the reason batteries get spent is because the reaction takes place. So a brand new battery will be like t equals 0. The moment you take off the 2 stickers at either end, if you take a brand new battery, or when you buy something new, they have a plastic in between, and you have to pull the plastic off. And that is equivalent to t equals 0. And then what happens is over time, the battery will get spent. And what that means is that equilibrium has been established. So to begin with, you have this taking place, and the reaction is going to go in the forward direction, right? So it's like as if you had only reactants, no products, not accurate description, but I just want to show you that it's going to take place in the forward direction. Reaction will proceed in the forward direction until equilibrium is established. When equilibrium is established, now your battery is spent. All right? And so what we measure is called the cell potential. At t equals, the instant the reaction starts, the voltage that you measure, or as the reaction continues, the voltage that you measure at that point is called the cell potential. Okay? So if we want to define what cell potential is, it's the ability, remember we said if you take galvanic cells push electrons through one end, so the anode pushes electrons out, the cathode pulls the electrons in. So if you want to kind of have a feel for what it means when we talk about cell potential, it's the ability of a cell to push electrons into the wire and to pull electrons. All right? The greater the ability to push electrons and the greater the ability to pull electrons to that wire, the higher the cell potential. All right? So if you want to define what cell potential is, the cell potential is a measure of the ability of a cell to push and pull electrons through a circuit. All right, so it is the ability to push and pull electrons through a circuit. And of course, the unit for this would be in units of volts. All right? Now, when we take galvanic cells, remember we're taking advantage of a spontaneous reaction. All right? If the reaction is spontaneous, then the reading that your voltmeter reads should always be positive. All right? And if ever in the laboratory when you do the experiment and you connect it to the voltmeter, like I said last time, if it's a spontaneous reaction, if your voltmeter reads negative, it means that you reversed the poles. All right? And so you need to reconnect it so that you reverse it and that you get a positive voltmeter reading. Okay? So if I take the Daniell cell, for example, if I take the Daniell cell, this looks at zinc, solid, going to zinc 2 plus aqueous, and we're using the cell notation, so we're going to say copper 2 plus aqueous, vertical line, copper solid. That will be the Daniell cell, the cell notation. It is always customary to write down the cell potential right next to it. So whenever you write a cell notation, you also will give the cell potential right next to it. So for this combination, the cell potential is 1.10 volts. All right? And when you deal with cell potential now, it turns out that the cell potential that you measure is related to free energy. So we're going to look at the relationship between cell potential and free energy. And as all of you know, for any reaction, so the reaction that we're looking at is this reaction. So if you look at the net reaction, we know that for this reaction, the symbol for free energy is the change in free energy is delta G. And if this is spontaneous, we know that the sign has to be negative. All right? If delta G is negative, then your cell potential has to be positive. Okay? That's why if you're dealing with a galvanic cell, you have to make sure that your cell potential is positive. Got it? And the relationship between the two is given by delta G reaction equals minus NFE cell. All right? So where delta G is the free energy of the reaction, N is the number of moles of electrons transferred in the reaction as given by the balanced equation. So if you take the Daniell cell, we know that 2 moles of electrons for the balanced equation, for every mole of zinc and every mole of copper that's involved in that reaction, you have 2 moles of electrons being transferred. And therefore, N would be 2. So it refers to the number of electrons being transferred as given by the balanced equation. Okay? Now, F is called Faraday's constant. Faraday's constant. And Faraday's constant gives you the charge per mole of electrons. All right? And this is a constant, and this has a value of 9.6845 times 10 to the power 4 coulombs per mole. All right? Where C equals coulomb. The unit for charge, remember, is coulombs. And so if you take the Faraday constant, it's a constant value, 9.6845 times 10 to the power 4 coulombs per mole. And what that gives you is the charge per mole. So we know the number of moles of electrons that are being transferred based on the balanced equation. We know that each of those electrons will have a charge of 9.6845. So the 1 mole of electrons will have that charge. And then, of course, we know that this is the cell potential, and that's the free energy. Okay? So if I take the example of the Daniell cell, all of you recognize that for the Daniell cell, so let's apply this to the Daniell cell. So example is Daniell cell. If you take the Daniell cell, the net reaction we know is zinc solid plus copper 2 plus aqueous, giving me zinc 2 plus aqueous plus copper solid. And I know in this, if I look at the half reactions, I know at the anode I have the oxidation, which is zinc solid going to zinc 2 plus aqueous plus 2 electrons. At the cathode, I have copper 2 plus aqueous plus 2 electrons, giving you copper solid. So by looking at the half reactions, I know 2 electrons are being transferred, 2 moles of electrons, because in a balanced equation, you can see that as long as 1 mole of zinc reacts to give you 1 mole of zinc 2 plus, you have 2 moles of electrons being given off. And at the cathode, you can see that 2 moles of electrons are taken up. So I know that I'm going to use, now if I want to calculate the free energy for this reaction, I know delta G reaction equals minus NF E cell, all right? And I know that N equals 2. We know that E cell for this is 1.10 volts, all right? And so F is a constant, and I can figure out what delta G for that reaction is. So I can say that delta G reaction equals negative, and then I'm going to put the 2 moles times the Faraday constant is 9.65 times 10 to the power 4 coulombs per mole. All right, so that's the Faraday constant. It's a constant. Since everything in this is like to 3 significant figures, I'm just rounding off the constants to 3 sig figs as well. And then times the cell potential is 1.10 volts. Yes, go ahead. Hold on, I may have made a mistake, actually. It should be 9.6485. What did I write down? 9.6. I got these two mixed up, okay? So it should be 9.6485. All right, so the Faraday constant should be 9.6485. Okay, so if you round this off, you'll end up with this, which gives you, so in an exam, I will not provide this equation, but I will list out all the constants. So I will give you what the Faraday constant is, all right? So you don't need to memorize the Faraday constant, but you do need to know how to use that equation. You need to know what equation you need to use if you're going to figure out. So you need to know this relationship, though, okay? So if you work that out, this would come out to be negative 2.10 times 10 to the power 5, all right, Coulomb volts per mole. All right, now it's important to remember that 1 Coulomb volt equals 1 joule. All right, because remember, free energy is always given in terms of kilojoules per mole. So we have to convert to the SI unit for energy, which is joules or kilojoules. All right, and the conversion from Coulomb volts to joules is that 1 Coulomb volt is 1 joule. So that means this equals negative 2.10 times 10 to the power 5 joules per mole. But remember, we always give free energy in terms of kilojoules per mole. Free energy and enthalpy change. Change in free energy, change in enthalpy is always kilojoules per mole. Entropy change is always what? Joules per Kelvin per mole. Okay, so that's the sort of the standard unit we use. So you want to convert this to kilojoules per mole and divide by 1,000, so you end up with negative 210 kilojoules per mole. All right, and your answer comes out to 3 significant figures. Okay, so let's say you're given an example where you're asked to calculate the free energy for a reaction, and let's say we're going to apply this to another example, and the example that we're going to look at is, let's say for this reaction, so we're looking at the reaction of N2 plus 3H2 gas, giving you 2 NH3 gas. And let's say that the cell potential for this is the potential for this is 0.057 volts. Okay? And let's say you're asked to calculate delta G reaction for that. Okay? So that means that if I wanted to calculate what delta G is, can you see that the first step is I need to figure out how many electrons are being transferred? All right? And so for this reaction, if you're going to figure out, we've done lots of examples where we figured out how do we know how many electrons are being transferred. So if I take this equation and I want to figure out how many electrons are being transferred, how would I approach this? It's going to be hard to split this into two half reactions. Can everybody see that? So in the absence of splitting into half reactions, what is the way in which we figure out how many electrons are being transferred? Just the way we balance redox reactions. What do I need to do? Oxidation numbers. All right? So you can see that I have 2 nitrogen atoms, but each will be 0 because it's an element in its natural state. Here you can see that I have 6 hydrogens. Each hydrogen atom would be 0. Over here I have 2 nitrogens. But now can you figure out what the oxidation number for nitrogen is? Each hydrogen is +3. So each nitrogen has to be what? -3. And then we have 6 hydrogens. Each would be +1. Okay? So now let's figure out which one is undergoing an oxidation. So if you take nitrogen, nitrogen goes from 0 to -3. Does the oxidation number increase or decrease? It decreases. So you can see that this decreases, and therefore it's a reduction. All right? And each one decreases from 0 to -3. So what is the relative change? 3. So that means it's reduction. 3 electrons are picked up. There are 2 nitrogen atoms overall, so 6 electrons are picked up. Got it? Now let's look at hydrogen. Each hydrogen goes from 0 to +1. So the oxidation number increases. If the oxidation number increases, we know it's an oxidation. Okay, so you've identified that's an oxidation. Now if you look at each hydrogen atom goes from 0 to +1. So what is the relative change? 1. So it's an oxidation. So we know 1 electron is lost per atom. How many hydrogen atoms are there? 6. So can you see that 6 electrons are lost? Now finally, you have to confirm whether that cardinal rule applies. You know, always for redox reactions, what's the rule? Number of electrons given up have to equal number of electrons taken up. So do they equal each other? Yes. So now we know that for this reaction, we know that N equals 6. We figured out that 6 electrons are being transferred. We know that E equals 0.057 volts. All right? So that means delta G reaction equals minus NFE cell, if you wanted to. That's negative times 6 times 9.65 times 10 to the 4 coulombs per mole times 0.057 volts. And that number comes out to be negative 3.30 times 10 to the power 4 Coulomb volts per mole, which is also the same as 3.30 times 10 to the power 4 joules per mole. Now I need to convert that to kilojoules. Divide by 1,000, you can see it comes out to 33 kilojoules per mole. I'm doing this relatively fast because, you know, we've done problems of this type before where you've dealt with free energy. We've completed thermodynamics, and you know what it means when we look at the free energy. Now, can everybody see if it's a galvanic cell, delta G has to come out to be negative. All right? So if it's not negative, you know there's a problem. Got it? Okay. So now we've looked at the relationship between the cell potential and the free energy. Now, the same relationship, if the reaction is under standard conditions, all right, now what we do is we put that little nod. Remember, delta G nod reaction equals minus NF E nod cell. All right, so if the reaction is taking place under standard conditions, then we would write this in this form, where E nod cell is the cell potential under standard conditions. All right, and when we say standard conditions for if we're dealing with galvanic cells, it means that all reactants and products are under standard conditions. That means if you have gases, gases are at 1 atmospheric pressure. Solutions are 1 molar. All right, so standard conditions are standard atmospheric pressure, which is 1 atmosphere. So if you're dealing with galvanic cells and you're dealing with standard conditions, then your reactants and products have to be under standard conditions, and that would mean if you have gases involved, the pressure of that gas has to be 1 atmosphere. If you have any solutions involved, that means it's got to be 1 molar concentration. So copper 2 plus or Fe 3 plus aqueous solutions should all be at 1 molar concentration. Now, what you want to finally, sort of an important take-home message to remember is that whether you're dealing with delta G, whether it's under standard conditions or if it's under standard conditions, we know delta G is an extensive property. All right? What do we mean by when we say thermodynamic quantities like delta G, delta H, delta S are extensive properties? You guys remember from last quarter, what does it mean when something is an extensive property? Who remembers?
It depends on quantity.
It depends on the amount of substance. Remember, an extensive quantity is like mass. If you double the amount, the mass doubles. All right? If you double the volume doubles. All right? And so an extensive quantity is any quantity that depends on the amount of substance. So if you double the amount you're using, then delta G would double. If you triple the amount, delta G would triple. Same thing with delta H or delta S. But when we deal with potentials, so if you take E cell or E naught cell, this is an intensive property. So even if you change the coefficients in a balanced equation and you double them, the cell potential does not change. All right? So an intensive quantity is like density. If you take a drop of water, the density is 1. If you take a whole swimming pool of pure water, the density would be 1. Do you get it? If you take a bucket of water, the density is 1. So density is an intensive property. It's independent of the amount of substance. All right? Likewise, when you deal with potential, potential is an intensive property. So if you write a balanced equation and you double everything, all the coefficients by 2, it does not matter. It will not affect the cell potential. So if you take the Daniell cell and multiply the coefficients for the net reaction, you multiply everything by 2, your cell potential will remain the same. If you multiply the coefficients by 2, your free energy would double. All right? Your enthalpy change for that reaction would double. Your entropy change for that reaction will double. All right? However, cell potential is an intensive quantity, and it is not affected by change in the coefficients of that equation. So that is an important point to remember. All right? So now that we've looked at cell potential and the relationship between free energy and cell potential, now we're going to delve into this a little bit more deeper. And we're going to look at what we call standard reduction potentials, or standard electrode potentials, or we call it standard potential. All of these terms are used to refer to the same thing. So it is standard reduction potential, standard electrode potential, or standard potentials. Okay? So it turns out that it is convenient. If you take the Daniell cell, what we measure experimentally is the cell potential, the overall potential when you combine the anode with the cathode, and the potential that you measure is the cell potential for the entire cell. it is convenient for us to split that into two parts, because sometimes it's convenient to know what contribution each of those electrode makes. And the reason it's convenient is that now if we can assign a value to each of the two parts, remember every galvanic cell is made up of two electrodes. You have the anode and the cathode, all right? And overall what you measure experimentally is the overall cell potential. However, just as a mental process for us, it's convenient to take that cell potential, the overall cell potential that we measure, and split it into two parts so that we want to look at what is the contribution that comes from the anode and what is the contribution that comes from the cathode. Does that make sense, everyone? Now, in reality, you can't measure that. That's not experimentally measurable. But what we're going to do is we're going to assign a relative weight to the contribution that comes from the anode and a contribution that comes from the cathode. Okay? So we're going to define this term called the standard electron potential, and we're going to say it is convenient to think of each electrode as making a characteristic contribution called its standard reduction potential. All right, so it is convenient to think of each electrode as making a characteristic contribution called the standard reduction potentials. It turns out standard reduction potentials are always written in the form of a reduction. Okay, so we're going to write everything in the form. So we're going to say that each cell has two components to it, all right? And we're going to look at the contribution that comes from each one of those. And that contribution that comes from each part is called the standard reduction potentials. And we, by definition, we always write the reactions as reduction. Even though at the anode we have an oxidation, we write everything as a reduction. All right? And the symbol for this is E naught. All right? And of course, the unit is volts. All right? So the symbol is E naught, and the unit is in volts. So it turns out that if you turn to tables, you will find tables where all of this is listed out. So these are called, so what you will find is if you turn to tables, you'll find what is known as standard reduction potentials in aqueous solutions. So you'll find these available in tables, all right? And just give me one moment to finish the topic, okay? So this is much like Ka values. Remember, you have Ka values for acids. All the acids are listed at Ka values, or pK values. Likewise, for all redox half reactions, you have standard reduction potentials, all right? And they're always written in the reduction form, because if we wanted oxidation, all you do is you reverse the sign. So overall what you do is, and I'll repeat this at the class next time, but I just want you to remember that if you're looking at the cell potential is the sum of the cathode, the contribution that comes from the cathode. And remember, cathode is the reduction plus the contribution that comes from the anode, but now we have to flip the sign because it's an oxidation. Remember, all these tables are always written in the form of a reduction. So we flip the sign so that now we end up with anode, all right? And in this way now, we can use these tables to add the contribution that comes from the cathode, which is the electrode on one side, and the anode, which is the other. And if you sum them together, that should give you the overall cell potential. Okay? So I will repeat this at the beginning of class next time and take lots of examples.